Okay, so our last speaker for today will be Rama Cont from Oxford. And Rama will be speaking about stochastic dynamics of limit order books, a journey through timescales. Thank you.
Yeah, thank you very much, Philip. So it's a pleasure to be here. And I would like to take the opportunity to show you some examples of problems coming from quantitative finance, where queuing systems and stochastic reflection and asymptotic methods such as diffusion limits are relevant and can be used to answer some interesting questions. So I'll start by explaining a little bit what the context of the problem is, and then show you why asymptotics is relevant in this type of problem. And then I'll try to show two different types of ways where these problems can be studied. One is to build the full dynamic models of the limit order book. So, okay. Yes, so the one approach will be to build dynamic models of full limit order books, and this will lead to spatial point processes and stochastic PD models. And then the other direction is so-called the reduced form models of limit order books, which we introduced about 10 years ago, and which lead to more tractable models and models related to reflected random walks and reflected diffusions. And then if I have time, but I'm not sure I will have time at the end, I'll talk about some open problems and lots of interesting questions which arise in these models. So what are we talking about here? Well, so the problems I'm talking about come from the modeling of electronic trading in financial markets. So in most financial markets, either stock markets or other markets like foreign exchange markets, buying and selling takes place through electronic trading platforms. So there is no human, trading with another human. There are algorithms sending buy and sell orders to some electronic platform. And these orders get matched. So buy and sell orders get matched. So if you're willing to buy, for example, a share of NVIDIA stock for 110, and somebody else is willing to sell at 109, then that works. They match your orders, and the transaction takes place, and that's fine. So these orders arrive at very high frequency, because there are millions of market participants sending orders in real time. So we have a very high frequency of incoming orders for buying and selling. And the rules are that, well, you can send two types of orders. One is you say, well, I'm willing to buy, but I'm not willing to pay more than 100, for example. You specify a limit, a price, and a quantity. I'm willing to buy 100 shares at price $100. Or I'm willing to sell 200 shares, but no less than $101. Those are called limit orders. And these orders wait until they are matched against an order of the opposite type. And then there are other types which are called market orders. These are orders to buy or sell immediately. Buy 100 shares at the best available price. That's called a market order. So you can think of then, so if you think now of this as a queuing system, well, at each price, you have people coming in to buy at that price. So these are think of them as the clients. And then at that price, if somebody's willing to sell, that will be the servers. So it means the buyers are the servers for the clients that are sellers, and the sellers are the servers for the buyers. So it's a kind of a symmetric type of queuing system. And so there are three rules in the execution of these orders. So first is price priority. If I'm willing to buy at a higher price than you, my order gets executed first. So this means that there are queues at different prices, but they're ordered in price. And this order, there's a spatial index, which plays a very important role, which defines the priority. Then there's a time priority. At a given price, the order which arrives first gets executed first. That's first in, first out rule. And then the third rule is that this best price execution. So this says that if they have, well, for example, let me show it. It's more easy to show. So let's say that right now I have these orders that are waiting to be executed. So these are the buy orders, and these are the sell orders in red. So currently the highest price to buy is this 21.5. Currently the best price to sell is 21.6. So these are called the best queues, or so this is called the bid price and the ask price. So the best buy and sell prices. So if I send an order to buy at a price lower than this, it will just sit in the queue. It will be added to one of the green queues. If I send an order to sell at a price higher than this, then it will sit in one of the red queues. But if I send an order to sell at a price that is lower than this, then it'll get executed immediately, but not at the price I send, at the best price. So the rule is because these guys have priority over these guys. So if I send an order, for example, to sell at this price, I'm not going to be matched with these guys. I'm going to be matched with this guy. So they get rerouted to the best queue. So this is the best execution group. So it means that orders can flow to both sides, but orders that flow to the opposite side in the middle get rerouted to the interface. This is very important. So that's called the best execution rule. Okay. This is not the only priority scheme. I'm just going to stick to this because it's the simplest. There are a variety of other schemes. One of the most interesting schemes, for example, to study is difficult, is pro rata execution. Pro rata execution means if I send an order to the queue, which is 50% of the queue size, any execution, I get 50%. So I can jump ahead of the others by sending big orders, and then I can cancel what so this leads to strategic, so I'm not going to talk about this, but this is also a very interesting problem. So one of the important aspects is that these orders can be canceled before execution. An order which has been executed is finished, but until the order sits in the order book, you can go and cancel. And again, we'll see this is non-trivial to model, and it plays a very important role. Okay, so at each point in time, when you look at the state of the market, you see something like this. These are the outstanding buy and sell orders. So buy orders in green, sell orders in red. And these show the orders which have not been executed yet because they have not been matched. So this is, you can think of this now as a queuing system, one queue at each price, and new orders are added to the queue, and orders of the opposite type serve the queues on the opposite side, but only at the best levels. And these best levels will move because when, for example, this queue gets depleted, so for example, here we have 3,000 orders to buy at this price. If I send an order to sell, which is 4,000, this queue gets depleted, and I move to the next one. So then this one will become a red one. So the interface between red and green constantly moves. This interface is called the market price. So the state of this summarizes supply and demand at time t. This changes every microsecond. And then the midpoint, which is the interface between the two, this is the market price. It also changes every microsecond. So of interest are, to understand how these things change, especially how the price moves up and down, what's the volatility of the price, how does the price dynamics, which is the interface between the two phases, relate to the influx of orders of different types, and so on. Yes. So if you send an order here, which is, for example, if you get, so for example, here I have 3,000 orders to be sold at this price. If you send an order of 4,000 at this price, not a market order, then it will get executed here. This will disappear. This queue will become red, and plus 1,000, which is the remaining. So you will be now the best queue of the red. Exactly. So, but you eat into the order book from the interface. Each one eats the other face. Okay, okay, so here are examples of, orders can be sent, and so you can set limit orders at a certain price inside the book. You can send a market order, which then eats into the interface, or you can cancel existing orders anywhere in the book. And one of the important things, I'll come back to it at the end, is that more than 99% of orders are canceled in less than a second. This is very important. If you don't understand this, then you don't understand the data when you look at it. So it means that the ratio of transactions to orders is less than 1%. Okay. So a lot of effort has gone into understanding this data. We have lots of data on this. We have typically microsecond level dynamics for this, which means for each typical stock over 1 year, we have terabytes of data, and then you have all the stocks. So you have really tons of data. So any model you write down, you can test it. You can do all kinds of evaluations on it. So there's lots of detailed data. And the interesting, so people have looked at this from a queuing perspective. You can think of this as a system of queues subject to this special execution and priority rules. And you can build simple models based on Poisson processes, more complicated models based on self-exciting processes, all types of models. So one of the things that one of the most important things here, which doesn't have maybe an equivalent in classical examples of queue system, is the price dynamic. So the position of the interface between the red and green defines the price. That's one of the things which is the most important here in these applications. Even if the order flow, the incoming order flows are Markovian, like a simple Poisson type model, a spatial Poisson model for the incoming orders, the dynamics of the interface will be path dependent because it depends on the history of what has been executed and so on. So that makes it a little bit difficult and interesting. Okay, so you can study simple models for the order flow, so spatial point process. And in these simple models, you can derive some formulas. For example, you can say the market orders and limit orders arrive at some rates, which depends on the price, but is independent of everything else. And the cancellations are proportional. Everything is independent. Then you get a birthday process. And for this case, which is the simplest case, you can calculate things. For example, if I put an order at the end of the best queue, how much do I have to wait for the order to get executed? What's the probability that the price increases first before decreasing? This kind of thing. So you can look at this kind of thing analytically, but the assumption that these simple models are simply not met in the data. For example, the inter-arrival times are not exponential. The orders are at constant size. So very quickly, people move to techniques which enable them to get rid of these restrictive assumptions. And the techniques are asymptotic techniques. So asymptotic techniques are very attractive here because you have a very wide range of timescales in the applications which we're interested in. So the elementary timescales where individual orders arrive are of the order of microseconds. So this is what I call the ultra high frequency range. So this is because we have high frequency trading, algorithmic trading. So really, or individual orders, when you look at the data, they take place at the level of microseconds. But most algorithms, most applications are interested in execution of a batch of trades, or things like the average cost of execution of a trade over, say, a minute. So already we are at a time scale which is 10 to the 6 times bigger than the elementary time scale. So there's lots of averaging going on here. And some problems involving portfolio management takes place over hour or day time scale, which is, again, around 100 to 1,000 times larger than the time scale in the middle. So you really have 3 well-separated time scales, and traditionally, different types of stochastic models have been used to model the price dynamics over these time scales. Now, asymptotics will allow us to connect the different but timescales and show, for example, why it's completely reasonable to use a well, at the very high timescales, at the very small timescales, everything is discrete. But at the daily timescale, you can model the price as a diffusion, and at the intermediate timescale, as we will see, the order book itself has a diffusive dynamics, and we can connect the parameters to describing these dynamics through asymptotics of these systems. So one thing which is interesting to do is to separate two things which are happening in the evolution of the system. One is the arrival of the new orders. So orders arrive and then they get matched. So the arrival is you can think of it as a match point process. It's orders arrive in different sizes at different prices. And then there's no constraint. Anybody can send an order at any price, anytime, and the orders can be big or small. So this is a spatial point process without any constraint on it. But then the shape of the order book itself is very constrained. So you can think of it as a pair of measures or a signed measure where the positive part is on the right, the negative part is on the left, and it has to have this shape. The red particles cannot be in the middle of the green phase. So it has a very constrained shape. The set of the signed measures of this type is not a vector space. It's a nasty state space. So you really don't want to live on this state space and define a process on this state space. It's not nice. So what we can do to avoid this non-vector state space is to say, well, let's separate two things. The arrival of the order flow, that's some market point process with no constraint. And then what happens once the order arrives? That's the market clearing. So the orders get matched to a specific rule. The order matching is a deterministic algorithm. It's the exchange looks at the existing orders and the new orders coming in. It determines which orders can be executed, executes them, and then it displays the new order book. So the second part is a deterministic operator. So this decomposition, okay, it's very easy to describe it in words. It also leads to a factorization of the evolution operators and the infinitesimal generators in the Markov case. And this is quite useful in studying this process. So you can model the order flow as again, unconstrained process. And the second operation here is a deterministic process which acts on an object which is the intermediate state. The intermediate state is the previous order book state plus the new order. This is not an order book. It's something which is not in your initial state space. It's in an enlarged state space. And then you project it back into the state space through a projection called the clearing operator. So, and the clearing operator is really something which is very intuitive. It will match the orders which can be matched because the prices correspond and their opposite sign. And it maximizes the volume of match orders. And once it does that, it just declares that the others are outstanding orders. Yes? Yeah, I'm not assuming that they have an existing distribution. This description applies to a controlled order flow, if that's your question. It's not static. It can. Yeah. It can react to the system. Yeah. Yeah. Think of a Markov model. In the Markov model, intensities react to the state. That's okay. Yeah. But this, I'm saying, I'm going to put this Markov model on the top floor, which is the market order flow. And then to construct from the market order flow the actual order book that you see, there is a clearing operator, which is a nasty nonlinear thing, but it's really simple to model. It's something that takes the orders, existing orders and new orders, matches them, and there's some thresholds and soups and imps and so on, which is not nice, but it's a simple deterministic operator. So I just describe it here. Market clearing by order batching. It's some operation that is done on these orders, and I stack it in an operator called C, and this will take care of the clearing. So now I focus on the order flow, and the clearing then projects it into this constrained state space. So this decomposition is nice because then, for example, if I model the order flow as a Markov process with some generator L0, then the order book process, which is the projection, is also a Markov process with an infinitesimal generator, which is can be decomposed with this as the L0, which describes the order flow. And then what I have is I multiply it on the left and right by two operators, R and C. C is the clearing operator, so it's lifted to functions on the state space, and R is the restriction operator, which restricts to the smaller state space. So these two are known objects, complicated but known objects, and they take care of the nasty things, and I can focus on what I can actually observe, which is the incoming order flow. So this factorization is useful for model estimation and design, for simulation, because I can simulate separately the clearing and the order flow, and also for the study of heavy traffic limits, because I have this diagram here. If I can show, well, typically studying the unconstrained order flow process in a heavy traffic limit is easier or easy. If it's a simple spatial point process, we know the limits because we have invariance principles or central limit theorems, things like that, downstairs where the order flow lies. So then if I can apply a continuity result to the limit of the order flow process, if I can apply the clearing operator and the restriction operator to the limit, then I can lift the results upstairs to something which will be the limit of the order book process. Okay, so this is something which, a technique, a trick, which can be used to simplify and get around this nonlinear state space problem. Okay, so let me show you an example of how these things can be used. So one approach is to look at continuous limits of this order book, where you send, so these prices are multiples of so-called tick, which is 1 cent. So if you think of 1 cent, a small compared to the price, which can be $20 or $100 or whatever, then there is a scaling limit where you take the intensity to be high. In practice, they're very high. You are orders arriving every microsecond, and then you take the tick size to be very small. And this double scaling leads to a representation where you replace the discrete queuing system by a pair of densities for buy and sell prices. So I call this density U. So big U is the order book, and U is small u is the density. And V will be the volume at the absolute price P. And if I center it at the current mid price S, I will call U the density at a distance X from the mid price. So this is, we typically look at the current interface, and we look at the distance X from this interface. So using this technique, one can show that if you start from this discrete model that I showed you earlier with the Poisson arrival rates and so on, you can show that this leads to an SPDE limit where the dynamics of the centered limit order book has the following form. You see that in this limit. So this is okay. So what you see here, this is one of the things I would show. What you see here is a mixed or hybrid limit where you have a fluid limit away from the interface, whereas at the interface you have a diffusion dynamics. Why? Because so in particle systems, you never see this, because in particle systems, you typically have translation invariance. If you have a scaling at X, you have the same scaling at X plus H and so on. Here, you have this best execution rule, which says that if I send a price on the opposite side, it gets re-injected into the interface. So it means that if you think of the case where orders arrive with the same intensity roughly everywhere, and you're in a box minus LL. Okay, let's not ignore infinity problems. And then if the mid price is in the middle, then roughly half of the orders will get re-injected at the interface. So it means that I will have intensity 1 at every point inside each phase, but at the interface, I will have an intensity of order L. And so if L is now sent to infinity, then you will have so you'll have a much higher frequency of arrival at the interface than inside. So it means that viewed from somebody, say an insect who lives inside the order book, he will see what's going on at the interface as something going on at very high frequency. Okay, so there's this, so the different scalings at the interface and strictly inside, okay? So you get a convection term towards the interface, and then at the interface, the two fluxes meet, and then there's an interaction which leads to a dynamics for the boundary, which is driven completely by the imbalance between the buy and sell flux at the boundary. If you work this out, you see that the boundary of this, so the price, what we call the price, will have will follow an equation which is of this type. It's driven by the gradients of these two functions on the right and left, and in general the gradient on the left and right derivatives but do not match, so you have a non-trivial dynamics for the boundary. So in this case, if you match this with the equation shown here, it will show you that the boundary itself is diffusing. So it means that if I put these three things together and I now look at the dynamics of the density in the fixed price, not the centered coordinates. This, if you apply here the Ito-Pencil formula, it gives you that the order book in the fixed price coordinates follows will satisfy an SPD, a pair of SPDs. So if you look at the left and right of the interface, with a moving boundary condition where the boundary is diffusing, but it's diffusing through terms which are determined by the gradient of the solution. So there are three coupled equations. This is a stochastic but moving boundary problem. So this is one type of thing that you can do with this stuff. So there are examples of this which are tractable. You can look at the diffusion type of models of this, and there's. But what you see from this type of model is that the action is really taking place at the interface. So another type of model is to zoom in on the interface and say, well, you know, we're not so much interested in the dynamics away from the interface because we're interested in the best buy and sell cues and the price, which is the position of the mid price in between. This is what we call a reduced form representation. So here we simplify a thing by looking only at the two best cues, and the position of the two best cues is determined by the price. So we have three variables basically. So we have three variables: the QA, QB, and then the price. Okay. So the idea is, well, if we have only two variables, these two Qs, what happens if, for example, this Q gets depleted? In the big picture, I move to the next Q. But if my state space is only the two best Qs, where's the next Q? So here we say, well, we can think of the rest of the order book as a reservoir. Okay. So think of your system is in stationary state. So there is a distribution of height for the next best Q. Let's call it F. So every time my best Q, which is my state, gets depleted, it goes to 0. I draw the new value from the distribution F because I'm taking a sample from the distribution of next best Q. So this means I can I have an effective dynamics for the best Qs, which is I follow the queuing system rules until one of the Q gets depleted. Then I regenerate it by drawing from this distribution F, which is supposed to represent the stationary state distribution of the next best Q. So this is a great simplification, which gives a lot of analytical tractability. So here it means that in addition to so we shrink the state space to really just two queues and one price, but then we add this parameter, which is this distribution f, which is supposed to be the distribution of the next best queue length. So this is what it looks like in data. There's a joint density of the bid and ask queues after a price move. So it's a new queue length once the price moves. What's behind the next, the best queue? Okay, so I'm going to just show you. So what happens now in this type of dynamics? Well, what happens is this. So you now look at the two best queues. So you are in the quadrant, in the positive quadrant. And so you start from here, for example. The queue length will diffuse. This is a tandem queue system at a very high frequency. So it's but typically has a diffusion type dynamics. When one of the queues hits zero, in this case, it's the bid queue, then you go to the next best queue, but next best queue has a length which has nothing to do with this one. So it jumps to a new point in the interior. So it means that every time you hit one of the axes, you jump inside to a new point which has a distribution f. So you jump inside and then rediffuse, jump inside and rediffuse. So you have a negative drift towards zero because you keep consuming, executing the orders. Once you deplete, then you take the next best queue, so you jump inside. So it's a discontinuous reflection. So it's a regulated diffusion inside the orthant with discontinuous reflection at the boundary. And in fact, you can look at it as a pathwise construction. So in addition to the square-hole map, which you would use for a reflected process, you need also a sequence of jumps, which tell you where to jump in inside. So the pathwise analog is, I give you a sequence of points inside the orthant. These are the points you jump to. Rn is the point I jump to at the nth hitting time of the boundary. And I could do a sequential construction of the reflection. Okay. So you can show that now this system has a heavy traffic limit, which is the one you would think of after having heard what I see. So under the assumptions that are the usual central limit type assumptions for the order flow. So the assumptions are central limit type assumptions for the order flow, again, the thing upstairs.